draw your attention over there. A week from today, master set 28. Dude. All right. Any questions?
What about master set 24?
We'll make that optional. If it helps you, I'll count it. If it doesn't help you, I won't count it.
Good, 'cause I'm trying to get it.
Because some people have done it. So we'll just say. That's for 54. So, bonus grade potentially. Other questions? All right, so in the 1890s, one of the Harvard physics professors recommended that his best physics students do engineering, because it was believed that physics was pretty much wrapped up. Just a couple of higher precision values to record, but there wasn't a lot left to do. Then
Is working. Yeah.
Then, in about 10, 15 years, special relativity comes out. 10 years later, the math for general relativity comes out. And also about this time, well, actually, shortly before special relativity came out, there was this idea of quantization and Planck. So, why was it necessary? Well, the idea was that if I've got, there's something called black body radiation, which is something that will absorb energy and won't give anything off. We can actually create objects that come pretty darn close to this by actually having a physically black object. And what they do is they have a hollow cavity in it, as if there's another kind of cavity. And they put a hole in it so that only certain radiation can leak out. Everything else is absorbed, but you have a little bit of a hole there so that radiation can come out. The prediction in classical physics, the stuff that we've learned, is that, well, pretty much you heat this black body up, radiation's bouncing all over the place inside. Some of it is going to escape, but pretty much any frequency of energy can come out of it. And so the prediction, if you look at crudely sort of energy coming out and frequency, is that, well, as the frequency increases, you have higher energy, and you end up with a curve that looks something like that. So if I take a black body and I heat it up, there should be so much radiation coming off of it that basically would kill anybody in the room. This is not what happened. Matter of fact, when they did experiments, looking at what is the frequency of the radiation coming off of it, yeah, it does pretty much match this, but then all of a sudden it dies off. So this is experiment, and this is classical physics prediction. Obviously, there's a divergence there. So first thing that Planck did is he looked at it and he said, you know what, let's just see if we can map this. Don't know why, but why this happens, but let's just see if we can come up with some formula that'll fit that. And he does. And since I can't do it off the top of my head, let's see, there's a couple different versions of it. That S, which is related to the energy density, 2 pi h over c squared f cubed e to the h f over kt minus 1 over 1, where h is some constant, and you got 6.62618 times 10 to the negative 34th joule seconds. So as the frequency gets bigger, this obviously will get bigger and bigger. But over here, we get e to the number that's getting bigger, minus 1. In essence, both of these start getting bigger and bigger, and the denominator will increase more rapidly than the numerator, so it shoots off to 0. And then you just have this constant up front. If you watch Stranger Things, there was at one point they needed the Planck's constant. And so the guy who's missing teeth calls his girlfriend from science camp. You know what I'm talking about? All right. They're trying to figure out what the first, I think, 4 digits were. Anyway, it's Planck's constant. So, great. He comes up with an equation, doesn't know why yet, so then he spends the next couple of years trying to come up with some justification for this being true. And in fact, comes up with this idea that not every energy, not every frequency of light is possible. That if only harmonics are possible, so flashback to harmonics, if I have 2 walls here and I have radiation bouncing up back and forth between them, I can have that marker fading. I can have a first harmonic there, or a second harmonic, or a third harmonic, and so forth, but only certain frequencies would actually work. And this quantization of it actually leads to this. When no longer any frequency of light is possible, but only certain frequencies of light are possible, then this equation comes out. Now, obviously, there's a big gap there, and it does require calculus and more math background, so we will leave it at that. Unless we want to spend the next couple of days delving into the joy of that. I'm going to sense, I'm sensing no, but there's an overwhelming desire, then we'll proceed. Okay. So, classical physics experiment, we now have this theory that works. Planck's constant turns out to show up again and again. There's also something known as Planck length, Planck time, which could be, for example, Planck time has 2 interpretations. Planck time is either the increment at which time progresses. That time is not continuous, but it does actually progress in quantized chunks. Or Planck time is the point at which our theories break down. And that something else is happening in time increments less than that, we just don't know what it is. Planck length, similar except for length instead of time. So we have this chunk in the armor of classical physics. The next one, the photoelectric effect. So they'll have some light source here. They'll have a metal surface, and then they'll have a detector right here. That's the detector. This is a light source, and this is some metal. So you shoot radiation at the metal. If I have an electron that's, I got electrons floating around outside this thing, it's going to eventually hit an electron, the electron will go shooting off. Detector detects it. So they found the following. The current, when I say current, we have electrons that'll be coming off of this, and those electrons coming off of it are current. That the current is proportional to the intensity of the light. If there is a current. If there is no current, then the intensity is irrelevant. I think it's A and T, it could be E and T. Irrelevant is one of those words there, right? I got spell check, tell me if I've done it right or not. If there is current, the backwards capital E means there exists. If there exists current, the current is immediate. It doesn't require building up to it. And then the last bit is to create current. The frequency of light is above some minimum threshold. And again, threshold, I can never remember if it's 1 or 2 H's, but we'll go with 1 for now. Or chances I wrote it down here. Oh, I have only 1 there. Okay. Now, the reason why this flies in the face of classical physics is the fact that that's not the way waves behave. I have a wave imagine you're at the ocean and a wave hits you. So there's a certain amount of energy in that wave. If the wave is bigger, then there's more energy into it. If nothing else, think of more potential energy in the ocean wave because you have stuff higher up. So if energy is related to how big the wave is, in other words, the intensity, I should be able to just crank up the light. If I have light that's not producing any electrons coming off of it, I should be able to crank up the light, and that would give me more energy, and therefore I should be starting at electrons, but it doesn't seem to work that way. This is one of Einstein's contributions. He speculates, well, if there's this quantization thing going on, as Planck had figured out, perhaps the quantization with light is the fact that it's not a wave, it's a particle. And the frequency relates to the energy of that particle. And people look at that and go, wait a second, it can't be a particle, we've done the experiment already. If it's a particle, the following should happen. If I take two slits here, and I send waves against it. So I have waves traveling this way, I have two openings there. If it's a particle, then it's either going to go through one slit or another. If it goes through one slit, then I should have a bunch of particles hitting here, go through that slit, then a bunch of particles hitting there. That should be the pattern if it's a particle. If it's a wave, I send the waves in, I've got my double slit. The waves should go through and creep through. Think of these as peaks of waves. And then this wave will expand, and this wave will expand. So the points where the two waves meet, we have constructive interference. The waves where one is peaking and one is troughing, we should have destructive interference. And what you should end up with, if I shine light against some sort of surface right there, I should have brightest in the middle, and then less bright, and so forth. And when we run this experiment, we see this. And it's simple enough. If we got a couple minutes, I could go and actually show that we get that. But Einstein's coming along and he's saying, wait, suppose we pretend it's a particle. That really seems to be an issue, but it works. For the information we have here, what Einstein speculates fits. So the energy of the light depends upon the frequency, not the intensity. All that intensity does is it sends more particles at that energy. And so therefore I get more electrons kicked off. But if I'm below that threshold, if I'm below the energy it takes to get an electron to shoot off, then occasionally I'm going to get hit by hot flashes here. All right, so if I'm below the threshold, I can send as much as I want, but none of the particles have enough energy to kick the electron off. So light seems to behave like a wave sometimes, and it behaves like a particle sometimes. And that opposes classical physics. Now, if you think about what I'm telling you right now, I'm basically telling you the stuff that I've taught you is wrong. What I'm actually telling you is that the stuff that I've taught you doesn't explain everything. Next, and I can do this derivation. All right, questions up to here before we actually get into some a little bit more math. One thing that comes out of this is that the energy of light, and typically when you're talking about light, this is the symbol that's used to represent light. It's the lowercase gamma. That the energy of a beam of light is equal to the frequency times Planck's constant. So if light behaves like a particle, then suppose I've got my nucleus right here, and I've got, that's my nucleus, and I got my electrons floating around. If if I send light in like this and it hits an electron and the electron goes shooting off, then I should be able to predict the energy of either, well, the light that's coming off of it. If I know the frequency of sending in, I can get a detector, figure out how fast that electron's cruising. I should be able to predict the energy of the light coming out using the stuff that we do in classical physics. So I'm going to treat light like a particle and apply our concepts of conservation of energy and conservation of momentum. This is known as Compton scattering. Right. So it comes in at some frequency, some initial frequency, and light's going to come out at some final frequency. Now I know that the speed of light should be constant going in and coming out. I know that the speed is the frequency times the wavelength. And that should, since it's the speed of light, should be c. And so frequency and wavelength are indirectly proportional. So I could equally write this as not only some initial frequency, but some initial wavelength and some final wavelength. Doing a little bit of algebra right here. Therefore, the energy of a photon is equal to h times c over lambda, because frequency would just be the speed of light divided by the wavelength. And so I have an alternate form, depending on if I'm dealing with frequency or wavelength. We are going to run into really bad notes here, or bad organization of notes, so I know I have it neatly written out somewhere. However, that seems